Hi, and welcome to Mr. Garofalo's podcast. In this episode, we are looking at factoring trinomials and polynomials completely. We're going to start by looking at exercise 3, part D from your classwork. In this problem, we're given a binomial expression, x to the fourth minus 16, and we're asked to write it in completely factored form. Remember, factoring completely indicates that we're going to have more than one technique or more than one step that we need to follow in order to find all of the factors of the original expression. So today in class we emphasized to always look for the GCF first. As I examine this, I see that this first term has an x, but the second term does not, so I'm not going to have a variable in the GCF, and the coefficient of the first term is a 1. The second term 16. That means the GCF for this expression is equal to 1. And remember, when we factor out a GCF of 1, we'll get the same expression back. So it would look like this, 1 times x to the fourth minus 16. So that didn't accomplish a whole lot. So I might want to think about, is this expression the difference of two perfect squares? So remember, any variables with even exponents are considered perfect squares. You see an even exponent on the x. 16, of course, is a perfect square. And we see subtraction, which would indicate the difference between them. So we should be able to write these as the product of conjugate pairs. We'll just need to think about the square root of x to the fourth and the square root of 16. The square root of 16, of course, is 4. The square root of x to the fourth is x to the second, since x squared times x squared would give x to the fourth. So our conjugate pairs will be x squared plus 4 times x squared minus 4. Now for most students, they would stop here thinking that they've factored the expression and they're done. However, as they examine each of these expressions, I might want to think, well, can I use difference of two squares again? Well, the first expression we see is the sum. This is even though these are perfect squares, x squared is a perfect square, as is 4, we see that as the sum of two squares. So we can't use that method on that expression. But if we look at the second binomial, we see that it is a difference of two squares. So we can go ahead and factor x squared minus 4 into two binomials. So we think about the square root of x squared, which would be x, the square root of 4, which would be 2. So we can further factor this into x plus 2 times x minus 2. This first binomial would come down to the next line. Now we're in fully factored form. We have 1, 2, 3 factors. They're all binomials. One of them happens to have a squared in it, but there's nothing we can do about that. There's no GCF here. This isn't the difference of two squares. Can't use trinomial factoring on it, so we leave that as x squared plus 4, and then we have our other two binomials, x plus 2 times x minus 2. So sometimes fully factoring requires us to use a technique twice. And in this case, we had to use the difference of two squares twice. Let's move on to example 4. Here they're asking us to consider the trinomial 2x squared plus 11x plus 12. And they asked us, do the three terms of this trinomial have a GCF other than 1? Well, let's look at the terms. The coefficients are 2, 11, and the constant is 12. Well, 11 is a prime number, so that sort of ruins things here. We might have had a chance at a GCF with 2 and 12, but 11 has no other factors other than 1 in itself. So there's no GCF for the coefficients. Let's examine the variables. We have x squared x. Oh, there's no x attached to 12. So the answer to this is no. The GCF is 1. Remember, when we factor out the GCF, we'll get the original expression back. Let's look at part B. Why would the guesses 2x plus 2 times x plus 6, 2x plus 4 times x plus 3, and 2x plus 12 times x plus 1 not make sense given our answer to A? Well, let's think about our answer to A. Our answer to A was that the GCF was equal to 1. Now, on the surface, these look like good guesses. In fact, if we think about the double distribute method, and we think about how that works, if we did 2x times x, we would get 2x squared. If we did 2 times 6, we would get 12. So that looks like a pretty good guess. Furthermore, when we look at the signs, we see the constant is positive. We also see that the linear term is positive, and both the signs and the binomials are positive. So these look like really good guesses. Why would they not make sense to guess? Well, let's go back to that answer from before. Remember, we said the GCF was 1. Well, look at the binomials that I'm about to highlight. All of these binomials have GCFs other than 1. For example, 2x plus 2 could really be factored as 2 times x plus 1 because there's a common factor of 2. 2x plus 4 could be factored as 2 times x plus 2. And 2x plus 12 could be factored as 2 times x plus 6. So let's think about the implications that has. If all of these expressions that are highlighted have a GCF other than 1, then why wouldn't the original have a GCF that is something greater than 1? It doesn't make any sense. If these have a GCF that are greater than 1, then we would have found it when we originally looked. So these guesses don't make any sense. We're not going to have an expression with any GCF. If there's no GCF here, then there should be no GCF in any of your binomial factors. So let's move to part C. If a trinomial does not have a GCF, so the original trinomial, then none of its binomial factors are going to have a GCF. And binomial factors, we mean these here. Okay? This pair, and this pair. So let's try factoring this by limiting our guesses. By limiting our guesses, so we're going to make sure that we don't have anything that has a GCF when we guess. So we're still going to start off with our typical guesses, our typical setup for a leading term that has a coefficient of 2x and x. We're going to have a positive in both, since we have a positive constant and a positive linear term. But I don't want to put any number in this spot right here. Okay? I don't want to put any number in this spot that has a greatest common factor with 2, of 2. So I think about some numbers that multiply to 12. We've got 1 times 12, 2 times 6, and 3 times 4. Now, of those possibilities, 12, 6, 4, and 2 all share a GCF of 2. 1 and 3 do not have a greatest common factor when paired with 2. So those are the ones I want to try. I want to try a 1 or a 3 in this spot. Now, if I put a 1 here, that means I would have to put a 12 here. Okay? Now, so how do we know if our guess is correct? Okay? Remember, we're going to do it through our double distribute process to check our work. So 2x times 12 would be 24x, and 1 times x would be 1x. That would be 25x. Uh-oh, I don't have 25x in the middle term. So that's not the factors we're looking for. So we're going to take this out. We're going to try the only other number that we thought made sense, which was 3. So instead of 1, we're going to try 3. So 2x plus 3, and the pair that would work there would be 3 times 4. We go through the process again. 2x times 4 would be 8x. 3x times x would be 3x. Add them together, and we have a winner, linear term of 11x. So notice, while it looked like we had a lot of different possibilities, there's 3 combos, and we could alternate them or put them in different spots. It looks like we had 6 possibilities. We really only had 2 possibilities. So we're able to limit our guesses by knowing that their GCF was 1 in the original expression. Well, hopefully this was helpful. I'll see you in class.